Welcome to the fifth episode of PodChat. Today we have Professor TP Singh with us. So, Professor TP Singh is a professor in the Department of Astronomy and Astrophysics at Tata Institute of Fundamental Research, Mumbai. He did his PhD from TIFR itself and postdoc from the International Center for Theoretical Physics, Italy. His main area of research is in quantum foundations and gravity. He has over 100 publications and recently been very active in the field of achions, octonions, and unification. Welcome, sir. Thank you for joining in.
Thank you. Thank you for inviting me. Thank you.
So, sir, let's start with a very interesting question. So, how long have you been associated to the academia?
Um, I joined for my PhD at the Tata Institute of Fundamental Research in Mumbai in 1984. So we could count from there. So that is about 37 years.
And sir, were you already planning to go in the academia? What was the first time when you decided that okay, I want to become a scientist?
So I finished my 12th class from Kendriya Vidyalaya in Ambala in 1979. And because a senior of mine had joined IIT, I was very influenced by him that yes, somehow I also want to get into IIT. I did not know what I want to do in IIT. I wanted to get into IIT and do engineering because we do engineering in IIT. So I got a rank of around 800 or something in JEE, and I joined IIT Delhi because that was the closest to where my parents live in Haryana. That's why we chose Delhi. And my rank allowed me chemical engineering. It did not allow me, the more sought after branches like electrical and computer science or mechanical. So what was left for me was chemical engineering. So very good. Whatever is available, you take. I joined chemical engineering. And first 2 years, those days, IIT BTech was 5 years. And first 2 years were common coursework, at the end of which we had to choose, join our department, which in my case would be chemical engineering. So I did those 2 years. At the end of the second year, I do not know what were the circumstances, but my interest shifted towards, you know, I wouldn't say physics, what you can call curiosity about the universe. How did the main question was, how did the universe begin? Why was there a Big Bang? So I must have read it somewhere or heard someone, I don't remember why. So I applied for a change to physics.
Okay.
So I got it. I got a change to do a master's in physics, integrated master's. But obviously, my parents were not very happy. My friends were also very surprised. They said I'm taking a very wrong decision. And I actually got scared. I went back to the dean and I said, can I change back to chemical engineering? They said, no, beta, these decisions are not taken in such a light way. Your seat has gone to someone else. Someone else has joined chemical engineering, in fact, from physics.
Okay.
And I know that person. I know the person. She's doing well in life. And interestingly, she also came back to physics later. So that is how I landed in physics. But I really enjoyed it. Maybe the introduction was through Feynman lectures I might have come across through some seniors. But those 3 years when I learned physics at IIT Delhi were really nice years because, I got to read on my own by going to the library, Feynman lectures, Dirac's book on quantum mechanics, principles of quantum mechanics. I had a good teacher who taught us the general theory of relativity. Another teacher taught quantum theory and introduction to quantum field theory. There were good mathematical physics courses on group theory. So it was that way a very rewarding period where one learns with fascination. So that was the whole period at IIT Delhi, 1979 to 84. And again, I was emulating a senior, this is Professor T.R. Seshadri, who's you may know. He's a faculty at Delhi University in physics. In 82, he came to TIFR for his summer program. I had never heard of TIFR. He came here for his summer project. Then again, it was like, oh, he went there. He said it is nice. So I will also go there. So, you emulate your seniors. So 83, I came to TIFR for the summer project. I was fortunate. They pre-selected me to join after 1 year for PhD. And whatever little plans I had to go abroad, I dropped because I really liked the institute. Professor Jayan Narlikar was here, and Professor Padmanabhan was also here. They were already very well known. I did my summer project with Professor Ajit Kembhavi in the astrophysics department. It was really a very vibrant atmosphere. And so they said, you can join us for PhD after 1 year. And also my parents were not well off that they can, pay for my application fees and my airfare to go to US. I did give the subject GRE. That far I went, but once I got TIFR, I said, why bother to make all these applications? This is good enough for me. Now, whether that was a right decision or a wrong decision, a good or bad, maybe we go through that as we go through the rest of the interview. Definitely a very interesting experience, and maybe all put together a correct decision to stay here. But those were that's for very specific reasons. I don't want to imply that everyone should stay back. It's very, very, very subjective. Maybe as we go along, we'll see the story. Well, that was your question. Right. How did I get into this? Yes, accident.
So when you were a child, as a student in high school or middle school, so that at that time there were no plans to go pursue science.
No, I remember. Okay, so that is very interesting. Depends on how you are brought up, where you are brought up. So I remember I was 7 years old and at my grandmother's place in Khanna, Punjab, district Ludhiana. That's where I was born. Okay. So that is the 1969 July, and that is when this the Americans NASA landed on the moon. So there was a radio broadcast announcing that man has landed on the moon, and I remember standing next to it glued. I was fascinated. It meant something to me, and I think that for me was an indicator that these things are exciting, that there is something out there. And the other event which was very important for me, my father was in the army. Now he has retired. So he was posted in Dehradun. So the cantonment there is called Clement Town. I think Clement in English, or Clement, how you say it. It means one place with good weather, opposite of inclement or inclement, whichever. It was really beautiful. There was a stream flowing through the cantonment. There were hillocks. There used to be lots of roses. It was very beautiful. So somehow that natural beauty really struck me that, this is something very beautiful. So I would probably couple that to, searching for beauty in nature in a more broad way. So probably, I think some inclination was there, and I'm very grateful to my parents that even though they had limited means, they put me in an English medium school where the education, happens to be better in some ways. more holistic. And that was for the first 6 years. After that, I shifted to Kendriya Vidyalaya. And fortunately, I was okay in studies. I was good, reasonably good in studies. And I remember one of my teacher telling me कि तुम मेहनत करो तुम बहुत आगे बढ़ोगे. These kind of inspirations that come from teachers have a very powerful influence on a child's mind. Yeah, encouragement. So in those years in Dehradun, I really had a wonderful time as a growing child, sensing something beautiful about nature. But then seventh onwards, I was in Kendriya Vidyalaya in various parts of North India. That was a normal schooling, but no indication that I had any particular interest in science. I just somehow wanted to study.
Right.
Although I was doing a little bit of sports for fun, like football, for example. But there was something that I must do well in studies. And I think that also comes, I think, if you're from a lower middle class family, where means are limited, and
Right.
you see friends around you in the school who come from more affluent families, there is something inside you that I can also do well. I
Right.
want to do well. So parents are very encouraging. Yes, you must study, you must work hard, you must do well in your class and all that. So that helped. I somehow I found myself to be a very studious. I don't know whether that's good or bad. I wanted to do well in studies. I was very fond of mathematics, but my physics was not good. I have made silly mistakes in my physics. I remember, maybe I'll tell you sometime. Very common sense errors.
Mhm.
So that is that. So after 12th, getting selected to IIT, and then the rest I've told you.
Right.
Then the TIFR phase began in 1984.
So, out of these 37 years, what was the best time that you've had? Like, if this wouldn't have happened, I wouldn't be here right now at this moment stage.
You mean academic discoveries or finding wise?
Or
Or
if any moment that changed your life, that any
okay, I think
significant.
one very fortunate thing is, I'm grateful to my institute and the people who supported me. I don't know whether I really deserved it. I was given a regular, a permanent academic position at TIFR just after my PhD,
Wow.
1989. So we don't do that these days. So that was very unusual. And I'm really, really grateful that happened. It gives me a position. My parents, I'm 27 years old. My parents, my father had already retired from the army. They retired early, as you know. And I was the eldest of four children. So they were concerned. When will you get a job? So fortunately, even before I went for a postdoc for 1 year to ICTP, Trieste, I had a job, and that has been a blessing. It gave me a platform to do my research, and fortunately, throughout my theme was that same question which first came to me around class 12 or early in IIT: How did the universe begin?
Right.
It is still the same question. I don't have the answer, but it has been an interesting journey. Throughout, I have been chasing that one question, and around the year 2000. Um, to answer this question, how did the universe begin? You need to have a quantum theory of gravity.
Right.
Everybody knows that. Possibly also unification. And those were the things I was trying under Professor Padmanabhan's supervision, and then beyond in the early years of my PhD. Around the year 2000, I became very frustrated with all these attempts, whatever was popular then. Um, I said, I don't like it. This is not how one should quantize gravity. So I gave myself a few weeks off to not calculate, but to think,
Mhm.
what is the problem? So then I had one realization that is in around the 2000. I still have it in my notes with a date that quantum theory depends on an external classical time. When you write down the Schrodinger equation, physics students will know there is a del psi by del t.
Mhm.
That t, that time, is classical. It is not an operator. It is not quantized. It is part of a classical world,
Mhm.
classical space-time. But classical space-time and classical bodies are a limiting case of quantum theory.
Right.
So the theory is depending on its own limit.
Mhm.
And that is not the most satisfactory way to formulate
Mhm.
the theory. You see what I'm saying? Yeah.
Right. Right.
So you have to have another formulation of quantum theory which does not depend on classical time,
Okay.
a reformulation.
Mhm.
That has been my theme I'm chasing since the year 2000. And since you asked, that is the turning point
Mhm.
in the thought process. It was very important to come to that realization and then chase it. I have not found too many physicists putting it this way, that there should be a reformulation of quantum theory without classical time. So they say, oh, if you remove time, how will you have evolution?
Right.
So, obviously, that is the question. I know that is the question, but you have to find answer to that question. So there are answers how to find that when you remove time, some other absolute time shows up.
Okay.
But that is what I call a turning point. And the other turning point for me, I mean, others may not agree, was in January last year, January 2021. I have it on my website. The date is January 7th. I derived the formula for fine structure constant
Mhm.
from my approach. The famous 1 by 137, which is
Right.
a mystery. So I believe that is correct. I'm still in the process of convincing others. For me, that was a big turning point, that I became confident that there may be some truth in the approach that I am following to quantum gravity. It's the same approach, reformulate quantum theory without classical time. So in the academic world, yeah, these were you can say, three major events: being given a job, permanent job at TIFR, then realizing how the main question of quantum gravity, in my opinion, and then this fine structure constant.
So you took a sabbatical for a year and then rejoined back as a faculty at AFR?
Yes, yes. I was there in ICTP. Professor Salam was there at that time, and Professor Dennis Shyama, who was at CISA and ICTP. Shyama was, of course, Dennis Shyama. He supervised Stephen Hawking
Oh.
and also was a close associate of Roger Penrose.
Wow.
Professor Shyama unfortunately died young, sometime in the 90s.
Okay.
Um, but very, very inspiring and affectionate, fatherly figure, very encouraging. So it was a good fortune to know him. So yeah.
So you said you have three siblings. So are they also into science or what are they pursuing?
No, I have a younger brother who teaches English in a school in Sonipat. He's very fond of his job. He loves to teach. And I have two younger sisters who are, homemakers.
Okay.
And there isn't really a close relative who is in basic sciences. A lot of people are engineering and doctors, but I I don't recall.
So, is there any specific thing you remember recall that as an outsider with no scientific background in the family and stepping into science? For example, if someone's parents are in science background, so they get kind of a little advantage, kind of that they can. So, what was that thing with you
Yeah,
that?
my parents were worried. Why are you leaving chemical engineering and going to, BSc physics that won't pay you so well? But they were kind to me. They had to sign, you see. They had to sign papers saying I approve my wards change from chemical engineering to physics. So my father signed, very supportive despite his fears. So obviously I'm extremely grateful to him that he let me do it. I don't remember whether the relatives said anything, but as they say, if you are successful, people say good things. Oh, he's a
Right.
scientist. Maybe nowadays, I don't know, scientist doesn't have such so much value in the country. I don't know. Maybe you can tell me your perception. But those days, if you're a student in Narlikar's group, then Narlikar is very famous, and even Padmanabhan. So he's a student in Narlikar's group, or he's a scientist at TIFR. So the people somehow then make a good image. Uh, I don't think I came across this that scientists are paid less and they are not as good or smart as engineers or doctors. There used to be a lot of respect and support for scientists in India in the 80s and 90s. Maybe it is coming down. You are young, so you will have a perception how scientists are. But there no opposition from, of course, colleagues also. But my supervisor, Professor Thanu Padmanabhan, who unfortunately passed away last year. He was also from a lower middle class family, similar, maybe very very limited means, but their family from Kerala, very academic. Father was Padmanabhan's father was very fond of mathematics, good at mathematics, wanted to do research in mathematics, but because of financial problems, could not. But really encouraged his son Padmanabhan to go in for mathematics, physics, whatever he likes. So we got along well. Paddy was only 5 years older than me. We got along well. Because the background was also matching. And if you look at the typical family background of TFR students and scientists, they are often from very modest background. So this problem is not there. You'll find so many people who are the only one in the family who is into science. So that way, the atmosphere here at TIFR in the 80s and 90s was very supportive. And yes, there's no problem.
And how is the administrative pressure at TIFR as compared to universities, public or private?
Admin pressure meaning
As in the administrative work.
having to contribute to administration.
Right, right.
I think there are enough physicists here and the job can be shared. If you don't want to do an administrative job and if you are doing serious science, you can justify your case. Oh, I have not, to be honest, done much admin work. Um, in fact, even teaching load has not been very high. I again have to give it to the institute that despite certain reservations I've had of late, I have been given all the time I need. 24/7, I can do my research. I live next to the institute. I have a good internet connection. I have decent campus housing and good institutional facilities. I couldn't have asked for more, you see. And if I don't want to teach or just want to guide students, that also I've been left alone. So I have these facilities may not have easily come abroad. Where in a sense life is harder, you see. But here, if you have a decent salary, you will get home help to look after the house. You know, the Indian setup. Your spouse can also work, and any help you want is available.
Right.
So this all the I have. If I'm not doing well, I have only myself to blame. So I have some reservations about how the academic system has evolved. Maybe we come to that later, or maybe we don't talk about it. But I have been given all my time to do my work, and that is how I could do it. You see, I'm really grateful to be paid to do my hobby.
Very nice. And what is the experience, or what is it like? How does it feel to guide a PhD student?
Yes. See, first thing I must say, the student must be good. I will not mince my words. The student who's doing theoretical physics, theoretical high energy physics, has to be good at mathematics, has to be good at mathematical physics, has to be good in their work, he or she, has to be very hardworking and sincere and love what they are doing. Not every student is like that. Not every student we are selecting are like that. But most of the, I guided 9 PhD students, almost all were very sincere and were with me because they loved doing what we were doing. Then it is a very positive experience. Um, I must add to that another angle, which probably is a revelation for many. No less importance I would give to my internship students who are not my PhD students, who are master's thesis with me for 6 months or a year. I have to say honestly that my unconventional, non mainstream research program has been pushed forward by these students in the last few years. And there's a reason for that. You know, a PhD student has to make a career.
Right.
I was in my early years of this program. I cannot put them, even though I might want to, in something risky. So they also know that they don't want to work on quantum foundations. They want risky means not enough job openings. Though I don't like those kind of circumstances. So my students worked on more safe areas, quantum field theory in curved space, conventional approaches to quantum gravity, black hole thermodynamics, cosmology, that kind of thing. And I did not, although they were very good, they have done well, they are well placed, I did not build with them that kind of heart to heart repo about my true research program about reformulating quantum theory, except in one or two cases.
Okay.
And they also thought that maybe this is too risky. So I didn't force them. Yeah, but you know, high risk, high reward research, some people should try. And I think I'm happy that it has gone on that path. So apart from my 9 PhD students, I've had about almost of the order of 50 internship students over the years who have actually done well. Some I have written papers with, and I'm very proud of these people. You see, many of them are extremely smart. They are in their fourth or final or third year in their integrated master's program or BSc final year. These children are very, very smart. They will learn quickly. They will check websites of various faculty. Quantum Foundations fascinates them. New approaches to quantum gravity. These kind of things, I think they have an eye for it. They
right,
will come and criticize me. They'll find out loopholes in what I'm thinking, help me. So this is a very rewarding experience, and there is also a lesson in it. Where will they go after such a internship when they go for their PhD?
hmm,
Not many people in the world are studying quantum foundations
right,
or new ideas in quantum gravity. Then it's a serious situation. All jobs or openings are in other more established,
right,
what you can call mainstream approaches to quantum gravity and unification. So we do have a problem, but interacting with good students, I emphasize the word good. See, if a student is not suitable for research, even if you are interested, please don't go down that path. You'll be frustrated. You need to get ideas. You need to be able to calculate and do mathematical physics. It is not for everyone, and there's no need to feel bad. You see, God has given us this or that kind of brain. God meaning nature. We have to accept it. I'm not good at sport. I'm not good at climbing Mount Everest or flying a plane, even if I want to. So I accept I'm not good at that.
hmm,
Find out what you're good at and do that.
Right. So, coming to quantum foundations, you said that why is it that many people are not pursuing this field? What is the restriction, or why is it the situation like this?
I think the main reason is that there is no experiment which disagrees with quantum mechanics up
okay,
until now. For most people, it would be that uh, if it agrees with experiments, I should try to push it as much as I can. That is not a bad viewpoint.
right,
But I think a theoretical physicist ought to be doing better than this.
hmm,
If you are not making a progress, quantum field theory is very successful for the other forces, electroweak force, strong force, lot of experimental confirmation. But the standard model still has 25 or 26 free parameters for which there is no explanation.
okay,
String theory tried but did not succeed. In the 80s, it was hoped that string theory will explain
hmm,
the standard model of particle physics. It has not done that.
hmm,
Despite 100 years of effort, we don't have a quantum theory of gravity.
right,
In my opinion, after so many attempts, if you are still not succeeding, you should be asking, are there any foundational loopholes
hmm,
which need to be addressed? And
right,
that is the path I took starting 2000. Till then, I never knew what is the quantum measurement problem. I'd heard it,
hmm,
but I didn't understand it.
right,
And I also, along with other students and colleagues, used to make fun of quantum foundations. It was a bad word, you see. Oh, he's gone into quantum foundations. Ah, he's lost it. That was the atmosphere. To some degree, it still is. But I learned, I read, I listened, I read Einstein. And by now, over years, I have come to appreciate Einstein's reservations about quantum mechanics. He's a genius, you see.
hmm,
He's not a disgruntled or disillusioned old man who was unhappy with quantum mechanics or disillusioned. Those are wrong words.
hmm,
It was very clear to him that quantum theory is approximate.
hmm,
That's what he says. It's not exact. It is an approximation to a more general theory, and we must find that theory. And you cannot find that theory by starting from quantum mechanics.
hmm,
You will have to start from somewhere else and derive quantum mechanics as an approximation.
right,
That has been a great inspiration for me. And for me, that is the same path,
hmm,
that there should be a way of quantum theory, writing quantum theory without classical time. This is how I interpret Einstein's reservations about quantum mechanics. So now, why is there a resistance to studying quantum foundations? I will be, I think, candid. It is a North American influence, in my opinion. You'll find very, very few physicists in the US who think quantum foundations is important. And I have read that that goes back to the Bohr-Einstein dialogues. Einstein is saying quantum mechanics is incomplete. Bohr is saying everything is fine,
Right.
complementarity principle. After the Second World War, when physics largely shifted to the United States from Europe, people didn't want any foundational conversations or debates of the Bohr-Einstein kind
Okay.
because they found it is not leading to any progress.
Right.
You are all the time talking about interpretations, measurement, wave function collapse, Schrodinger's cat, but are you making progress? That's a good point, actually. Had there originated philosophically this phrase, shut up and calculate.
Right.
It was very right for the start period starting after the Second World War because lots were happening. New particles were being discovered,
Right.
neutrinos, other things, cosmic rays, muons. Quantum field theory was very successfully coming up, and Bohr sort of won. Let us develop quantum field theory, let us calculate, and very successful. See, gauge theories, then came electroweak theory, QCD for the strong force. But notice there's a break. After around 1970s, if you notice, the standard model is where it was. It was ready then. And we have found some more particles completed it, top quark, and the Higgs. Higgs was found later in 2012. But what is going on after 1970s? Uh, Quantum field theory, in my opinion, as far as the standard model is concerned, is stuck. We have learned great deal about techniques and applications of quantum field theory, including to condensed matter, but it doesn't seem to work for gravity. That is 50 years of being stuck, a very brave attempt by string theory, which in my opinion has not succeeded. At least you can say has not succeeded so far.
Right.
Some string theorists will say it's young. It's 50 years old, but it is young. Give it another 50. Okay, take another 50. But at least tell me why is it not working? You don't have a reason why it is not working. I claim I know why it is not working. It is because you have not asked these quantum foundational questions, which say I and some other physicists are asking. So it is like, you are like this on pendulum was at one end, quantum interpretations. It swung to the other end, shut up and calculate. It is overgrown. It is too much still there. Friction, inertia. People still want to shut up and calculate. And I have a joke. Professor is saying, shut up and calculate. And student says, there is nothing left to calculate. That is where it is, you see. You are calculating, you are, as Hassenfelder says, lost in maths, but you are not making progress towards unification of gravity with other forces or quantizing gravity. Now, maybe people understand it, but it's a sociological thing, an economic thing. People want to keep on having their jobs, getting their grants. So I'm unhappy with my American theoretical physics colleagues who keep insisting that all is well with quantum theory. It is exact. It is not approximate. So whereas Europe is little more open about this, but very few physicists like Stephen Adler, Sheldon Goldstein, and a few philosophers in the US who seriously believe that quantum theory is approximate. And US, as you know, has a very strong influence. They have funding, they have PhD positions, they have the world's best universities, they have students, postdocs, a lot of good faculty. If they as a whole continue to believe that quantum theory is fine and quantum foundations is not a very important subject, it influences the rest of the world, including India. You will hardly find anyone asking such quantum foundational questions in India. Europe is better. There are a few groups, there are important experiments. I mean, I appreciate Europe for retaining that philosophical aspect of theoretical physics research, which, in my opinion, is much less appreciated in the United States. Perimeter in Canada is an exception. It's more open. So your answer to this question, why people don't appreciate quantum foundational questions more, they're not thinking. They're not thinking long enough or hard enough. They're not asking why have we failed? Why have we not been able to and there are groups, you see. There's a group on causal says, there's a group on dynamical triangulation, there's a group on loop quantum gravity, a very strong group on string theory. They're not talking to each other. They're not talking to quantum foundations people. So one student wrote, academia is broken. This is what I take broken to mean. Everybody wants to quantize gravity, but they have different ideas how it should be quantized, and they don't talk much to each other.
And why is this communication gap?
Why they don't talk?
Right.
Not that they don't want to talk. We have to publish. We have to satisfy our grant requirements. And maybe we are often extremely stubborn that my way is the correct way. This competitiveness and lack of experimental evidence for departure from quantum mechanics, lack of experimental evidence for quantum gravity. But I have a different way. I said, look at the standard model. It has 26 free parameters. We don't understand why it has this particular symmetries. This is data. The 26 free parameters of the standard model are data. You have to explain it. You have to explain why the fine structure constant is 1 by 137. And if you are not able to explain it, then you need to think. That is what I call foundational question. Why? What has gone wrong in my theory because of which I am not able to answer these questions about the standard model? And now a new line has come up. Some people have started anthropic principle and multiverses. There are many different universes in which fundamental constants take different values. And fine structure constant is 1 by 137 in our universe because otherwise we won't be there. Anthropic principle. This is not physics. Where are the other universes? We have not seen them. And can you show that there will be different values? What is the probability? This is not physics. Physics would be asking foundational questions. Could it be that quantum theory is approximate? That is the path I have been chasing for 20 years. And at least I would like to believe that I've had some success in the last couple of years. I'm quite happy with where I am.
Great. And regarding this paper that you have published last year regarding the constant, so can you describe in very basic terms that the derivation part in terms of, so that even like in layman terms, how that constant
Where
came?
are the values of these constants coming from?
Right.
Yeah, that is a very interesting question. Thank you. And the answer actually is not difficult conceptually. It goes back to this same question about the conflict between quantum mechanics and the classical world. So the classical world is made of these large objects, stars, galaxies, and planets, and space and time. Space and time are also classical, simply meaning that you can say that this point in space has these coordinates, say x, y, z, t, and they commute with each other. X times t is equal to t times x, x times y. On the other hand, you have the quantum world, where classical laws, Newton's laws of motion do not hold. Position and momentum do not commute. They become operators or matrices. Q times P is not equals to P times Q. How can it be that space-time on which quantum particles like the electrons live, that space-time is classical and the particles are quantum?
Right.
This is a contradiction.
Yes.
People will tell you, no, that is because gravity of an electron is extremely weak. But something is being lost there, which is what I think I have tried to overcome. That a quantum system which is in a superposition of two position states, like an electron here and an electron there, it will produce a gravitational field which is a superposition of two gravitational fields.
Right.
One as if the electron was there, another if the electron was here. You see what I'm saying?
Yes.
So it is like, now if the gravity is weak, it does not follow, I can argue that when the gravity is set to zero, the space-time is just ordinary flat space-time of special relativity. It does not follow. Because as if I look at the position there and I let the gravitational field go to zero, I'll get a space-time which is determined by that location.
Right.
And if it is here, so the limiting space-time is a superposition of two different flat space-times.
Okay.
Now that may look very counterintuitive because two flat space-times are identical. What does it mean to superpose them? I can help you visualize that in the following way. That point x1 and point x2 will no longer commute. That's the kind of, even if an electron at low energies is in a superposition of two places, the space-time which it produces has points which no longer commute with each other.
Okay.
That is much more natural. That is it is still flat space-time, but it is a more fundamental description of flat space-time, what is called a spinor space-time or a twister space that Penrose invented. If you are familiar with the Dirac equation, Dirac derived his equation by taking the square root of the Klein-Gordon equation, because only then you can describe fermions like the electron. So we took a square root of the Klein-Gordon equation, but we forgot to take the square root of flat space-time.
Okay.
I don't know if it is making some, it's just a bit technical, is it? A quantum system which is in a superposition of position states will produce a space-time which is also in a superposition of different space-times.
Okay.
And that is not flat space-time even in the low energy limit.
Order.
It is what we call a spinor space-time. That is my main progress, that instead of describing flat space-time using real numbers x, y, z, t, I found a way to describe it using non-commuting numbers known as the octonions.
Okay.
So there are only 4 kinds of numbers in which division, multiplication, addition, and subtraction is possible.
Okay.
The real numbers, which we use to describe space-time, the complex numbers, which also commute with each other, and the quaternions and the octonions. Uh, in these 4 and 8 dimensional numbers, different directions do not commute with each other.
Okay.
Now something extremely interesting happens. Suppose you put an electron and a quark in the octonionic space. So first you put it in our ordinary space-time. The electron and the quark, their charges have no relation to each other. Only from the experiment we know that the down quark has a charge 1/3 that of the electron. The moment you put electron and quark in the octonionic space, these non-commuting properties of the space-time itself tell you that yes, the quark's charge is 1/3 that of the electron.
Oh, great.
The space-time starts putting constraints on the particles because of its non-trivial structure. It is still a flat space-time only,
Okay.
but a more fundamental description of flat space-time, which if I average, I will get my ordinary flat space-time, Minkowski space-time.
Okay. Okay.
I wonder if you get the picture. There is a description of flat space-time which is more fundamental than its description using real numbers.
Okay.
And the description normally we have is based using vectors, which are analogous, say, to the Klein-Gordon equation or Maxwell's equation. However, particles like electrons are fermions. They are described by mathematical objects known as spinors, which are different from vectors. They're like square root of vectors. So I'm saying when you have fermions, you should describe space-time also by spinors,
Spinner. Yes.
not by vectors. When you describe the space-time of fermions by spinors made from the octonions, it seems that all these 26 parameters of the standard model will now get fixed.
Oh, great.
They are not free. It is like if you look at water in a bottle and you see Brownian motion of a pollen grain. You won't know why that random motion is happening until you look closely and you see there are molecules hitting randomly. It is the same thing. Look at Minkowski flat spacetime very closely and you see structure because it is described by spinors. And try putting electrons and quarks there. You will be forced to conclude quantization of charge. That is where the value of the fine structure constant comes from.
Okay.
You see what I'm saying?
This is very kind of revolutionary work, if I can say.
I would like to say that, but we have to convince the community. I think it's very important.
So why is it that you're not getting like support from your colleagues on this work?
Colleagues meaning at my workplace or in the community?
Like even your workplace and the community, there is kind of lot even the
Yeah, my workplace, I would be honest, is string theory dominated. And we have a very strong clash of ideology. String theorists, as I told you, would like to believe that string theory is the ultimate theory of nature and that quantum theory should not be modified. In my work, quantum theory automatically gets modified because I write it on this octonionic space. I don't write it on ordinary space-time. So, and there is resistance to that. Okay. Why? I don't know. Maybe it's just ideology. Lot of human sociology, ego, human ego, arrogance, not listening to the other person, all that comes into play. So I'm not happy, but there is slow response coming from Europe say a little bit from Russia, but not much from the US. They are very rigid. So they tell me that my work is too speculative, it is vague, it is not rigorous. So there is a conflict going on.
Right.
I'm saying it's rigorous enough, come and argue with me, but they
Right.
don't want to talk. It's like, if you don't look, you can pretend that it is not there.
Right.
So let's see how it plays out. I'm satisfied with the work. I'm not sad happy with the resistance offered by journals. We have another big problem in India. We will not accept something unless the West accepts it. We
Right.
don't think much for ourselves. That also upsets me. You know, I have all the freedom here in TI for all the time. I don't have to ape the West.
Right.
It's true, quantum mechanics came from there, relativity came from there, but it does not follow that quantum gravity will also come from there. We are stuck. Think, we have to think.
Right.
So, to summarize what I was saying, it is usually said and believed that quantum gravity effects on the standard model are important only at the Planck energy scale. I'm saying this is wrong.
Okay.
And Penrose would support what I'm saying because he has been saying the similar thing that even at low energies, if a quantum system is in a superposition of two position states, you no longer have classical time because two spacetimes have been superposed. So the concept of classical time and a classical clock is lost.
Okay.
And hence, one should work with a non commutative spacetime, which I found is the one described by octonions.
Okay.
So, electron does not live in four-dimensional spacetime, it lives in an octonionic spacetime. And from the octonionic spacetime, you can build the four-dimensional spacetime.
Okay. Got it.
And this is important even at low energies like at the LHC. So the reason why there are so many free parameters in the standard model is because we are not describing quantum spacetime the way it should be described.
Okay.
Now, this is a new idea. Some people are beginning to see its significance, others are ignoring it. I don't know why. So it is in that's in a state of flux. There is resistance. When a referee rejects my paper, they just will say things like, "This is hand waving. It's numerology. It is speculative." So
Uh,
it's an idea in who it has been presented. Some of it is published, and there is also resistance. So we'll see how it evolves.
So I was watching a video where they were talking that this peer review system, like how science is different from academia, like a cat in peer review system is kind of academic structure. So that is useful, but we shouldn't entirely depend on it. So we should give way to new ideas so that they can also be published. Because if some already expert, it does not exist to particular field because that is new. So obviously that won't be peer review.
yeah.
Right.
And blind, one-way blind peer review. The reviewer knows who I am, but
Right.
I don't know who the reviewer is. So, face-to-face, frank dialogue is not possible. A reviewer who's anonymous will say things which he or she will not say to me face
Right.
to face.
Right.
They
Right.
face to face, it was a very interesting idea. Please pursue it. You know.
So when you get upset or when you want some time off away from this academic structure, so what do you do? What are your hobbies and how you spend your free time?
I'm not a good model or example of hobbies. It changed over age. When I was younger, there was more traveling, going to places with good natural beauty, maybe playing some tennis. reading a lot of literature, including popular science books. But right now, I maybe become more lazy. That's why I'm not a good model or not a good example. I just am thinking about my work all the time. I will just lie down and sleep and doze and, daydream, maybe do a little bit of exercise or try to play the keyboard, but little things. I don't have any great successful hobbies which I've developed. People should not be like this. People should have hobbies. Many people do. They will go mountain climbing. But I find myself in a very strange situation. I'm going to be 60 this year. That is when they say that, your physics is all done. You should have done it before you turned 40. You won't get anywhere now. But I find that, no, this is my best time. I started when I was 40. That is when I had my good idea that there should be quantum theory without classical time. I'm not very bright, it takes time. 20 years have passed, but it is now bearing fruit with the help of students who calculate. Sometimes I do the fine structure constant calculation I did myself. But that is because I had an idea which I believed in very strongly, and I think it worked. And my situation is peculiar. I'm not saying it is great or not great. Many physicists at 60 might be slowing down, but not everyone. There are others who work till 80, people far, far better than me, people like Steven Weinberg, working till 88, you see, working till his last few months, and many other such examples.
And recently, a Nobel Prize was announced, and the person who was awarded on the telephonic call, he said that I am 93 and I am still working on a solar energy paper.
Yes, yes. There are, as with medical science advances, people's health improves. There is medicine to keep you going even if you have some problem in old age. So I am beginning to believe that at least in theoretical physics, probably true in experimental physics also, there is no age limit. It's up to you. If your brain keeps working, you work. Maybe your brain will not work that long, but
Right.
what happens to most people? They lose steam, they lose interest.
Mm.
And that's upsetting. You see, you'll find many such examples in India and maybe elsewhere. You get an award, you want to become a director, you become more interested in administration, you leave physics to younger people. But that's a choice we made. Maybe it's not, I think it's not a good choice. Yeah, older people in research institutes have to continue to be excited about physics like they were in their younger days so that they can inspire younger people. Why do our young aspiring researchers prefer to go abroad? They don't find us inspiring enough.
Right.
Who will not want to stay in their own country, close to
Absolutely.
their parents and family?
Right.
The Americans get to stay in their country, they don't come to India. Our students would also love to stay here, but
Right.
unfortunately, we are not able to inspire them. And that is our failure.
Mm. Right.
And that is because, I don't know, someone said that because we are a developing economy, research is also a career. We have to have a reasonable amount of money. And with that, maybe decoration, awards, promotions, directorships, vice chancellors. So research becomes a career, and Einstein would say that research is a noble exercise provided it is not your means of earning, which is a good point.
Right.
Suppose you had some other way of earn, you were very rich and your family was taking care of your living expenses. Then if you do research, you will not be in the rat race in that sense in terms of grants.
Right, right. and then they have this liberty to even explore these new ideas, this so-called risky things that.
Yeah, so it's not a good situation. It's too fractured.
Right.
I don't see what will bring us out. I have no idea. And what we are eventually going to need is an experiment which overthrows the current dominance of relativity and quantum mechanics. I think that will happen because there are reasons, very strong reasons in my mind to believe that quantum theory and relativity both are approximate. And I would like to believe I've made some progress. But who is to say how all this will shape up? I don't know.
Right. So that would be a very good point to end the discussion. And before that, I would like to ask you, what would be that one life lesson that you would like to give the young career researchers or even students who are entering this field of research in theoretical physics or in general?
I would place maximum emphasis on academic honesty, by which I mean ask your questions, look for honest answers, don't go by what others are saying. If you want to answer the question, why does the electron have the mass it does? Go ahead, ask that question. Find your answer, not someone else's answer. Unfortunately, this is hampered by, as I said, you need funds, you need salaries. So there is a contradiction. You land up doing, young people land up working on older people's ideas. That is the only way they will give you a salary. But as far as possible, I would still say, if you can face the pain and hardship, follow your line of thinking. Contest the system. Only if we contest the system can we break it. When you go for a PhD, it should not be that your PhD has to be on your guy's idea. If you are good, you should be given 5 years to explain the mass of the electron. Maybe you will make some progress, and then you should be given a postdoc according. So follow your line of thinking honestly, and I would say protest the system. Say, I've come here to do my PhD, you have selected me, but I will work on my idea, not yours.
Right. Thank you so much, sir. So it was a very intriguing discussion, and thanks for explaining this your work. Especially, I would really look forward to that the community supports you in that particular work. To me, it sounds really revolutionary to have that all figured out. Thank you so much for joining.
Thank you very much for having me. It was a pleasure talking to you. Thank you.
Thank you, sir.
Hope you loved the episode. Subscribe to our show and see you next Saturday.